And
No, that's not. No, no, it's like basic algebra.
I probably do.
Is that too dark with, is that not light enough? Those of you that are sitting in the back, you might end up finding that you're better off if you move a little bit forward so that you can see what's on the screen. I'll try to change the, resolution or whatever it is. And it doesn't look like I'm gonna be able to get much. Okay, so here's the way this is going to work. I'm going to write out before each lecture a set of class notes that I'm going to be working from, lecture notes that I'm going to be working from. And those will be on the board while I talk. I'm going to send you an email so that you have all those files. So anything that's recorded here is recorded here, and you don't necessarily need to be in a rush to scribble it down as we're working. If you can sit towards the front of the room, you can have a better chance of seeing this. If you get back, you might not see it. But so the point is that you'll have everything that you see from the board. You'll have all of those notes. So do record your own notes. Maybe just record what's relevant so you can kind of keep your ears peeled and try to pay attention to what the heart is of the conversation we're having. A lot of times, if you're too busy writing things down, you miss the point of what was being said. Well, give you the notes so that you have the time to pay attention to what I'm saying. Normally I'll get these into your hands before class starts, so you can just print out a copy and bring them to class if you'd like. This time through I wasn't able to do that, so I'll email the notes to you after class. We're going to do things just a little bit out of order, not entirely out of order. We're going to skip ahead on some conceptual stuff that is in later chapters. We'll discuss it now because it kind of helps to develop some of the arguments that we want to develop. We're going to be looking at kinetic theory of gases, which discusses molecular interactions. It basically models an ideal gas as a system of particles that are traveling with some average velocity, and their velocity regulates how frequently and with how much power they collide with the walls of their container, and this ends up governing the pressure. And so we kind of got our introduction to that in week one, where we looked at the balloon full of gas and asked what happens to the pressure as the volume changes or the temperature changes. Kinetic theory of gases is basically just a more in-depth look at that behavior. To understand some of the equations that we find in kinetic theory, we need to go back to the Boltzmann distribution, or forward to the Boltzmann distribution, which gets covered in greater detail in a statistical mechanics class, but shows its face in thermodynamics so frequently that I think it's suiting that we address the Boltzmann distribution first. The reason we need the Boltzmann distribution for kinetic theory is the Boltzmann distribution will tell us, based on temperature, essentially, how much energy is stored in a system of gases, and therefore what their average speeds are. Boltzmann distribution doesn't relate only to what's that called? Translational energy. Any partitioning of energy follows the Boltzmann distribution. So for those of you that are aware that molecules have translational kinetic energy, rotational kinetic energy, vibrational kinetic energy, the Boltzmann distribution is also used to look at those. Right now, we're just using the Boltzmann distribution to look at translation energies. And so the question becomes, what is the Boltzmann distribution? Why do we need it? What does it do for us? And the answer is actually fairly simple if you just simply say it, but if you try to look at the math and read it for the math, it becomes a little more complicated. The critical equation that we're going to be looking at, or the key equation in the Boltzmann distribution, is this guy right here. And this equation says that for a system of particles, that has a total number of particles, n. So that's our total particles in our system. If we've got a mole, then that number is 6.022 times 10 to the 23rd. For a system of particles at a particular energy level, how many of those, not at a particular energy level, but at a particular temperature, how many of those particles have a given amount of kinetic energy, or energy in general? Boltzmann distribution again refers to not just translational kinetic energy, but rotational vibration as well. So the question it answers is, given a system of particles at a particular temperature, what is the distribution of those particles in their available energy states? Now, it shows you that, well, let me think how to say this better. Imagine this. We've got 10 particles, right? And 1/10 of those particles have energy I. How many particles have energy I? One, right? So we multiply the total number of particles by this ratio, 1/10, and that tells us how many particles have that particular energy. Well, that's exactly what the Boltzmann distribution does. The Boltzmann distribution creates that same multiplier. We took total number of particles 10 times fraction in a particular energy level and got number of particles with that energy level. The n here is analogous to that 10. That's your total number of particles. E to the negative e sub I over kt divided by z. So if you just take those guys and stick them together, that's analogous to the 1/10. So this e to the negative e sub I over k, or e sub I over kt divided by z, that's what is analogous to your 1/10 ratio. So if you multiply this by your total number of particles, that'll tell you how many particles have energy level e sub I, right? So this thing z is called the molecular partition function. You'll find this out as you move on later. We don't need to know it for this class. You certainly don't need to know its name, but I'll tell you a little bit about it. What the molecular partition function does is it looks at a system of particles and it asks the question, it answers the question, how many different energy states are available to this system, right? And so it itemizes essentially all of the different ways that a system can store energy. If a system is only an ideal gas, then it only has translational kinetic energy. If it's a diatomic, then it can vibrate and it can rotate, etc. But the partition function z essentially is a function that itemizes available energy states. And so, take your e to the negative e sub I over kt divided by z, that's your ratio, multiplied by the total number of particles, and that's the number of particles that you have at a particular energy state. A couple things. The e sub I in the numerator of the argument of the exponent implies that as you move to higher energy states, as the energy of the state increases, the number of molecules in that state begins to decrease exponentially. So hold that thought, we're going to talk about why that is. And the t in the denominator of that exponential argument essentially, as T gets larger, the total decay becomes smaller. And so the implication of that T in the denominator is that at higher temperatures, the populations of states will increase. Right? So that's functionally what the Boltzmann distribution does. And I'm going to try to tell you why it does that or how it does that. We can't look at the math is way too complicated. But I'll tell you this. What will I say? If you have a situation where you've got a certain number of molecules and a certain amount of energy to disperse amongst those molecules, you'll get many different possible ways that you can store that energy. But of all of those ways, one of those ways is going to be the most likely state to find the system in. And the Boltzmann distribution does some statistics to eventually figure out which of those arrangements is the most likely arrangement that your system will find itself in. And once that arrangement is found, you can look at what the energies of the system would be in that arrangement, and you can predict that in real life those will be the observed energies of the system. So the Boltzmann distribution picks out the most probable distribution of energies through the system. Let's play with that concept for a second. So let's say I've got 10 joules of energy and I've got 5 particles and I have 4 states. Okay. 10 joules of energy that I need to split amongst 5 particles, and each of those particles has 4 different potential states that it can be in that have different energy. I'm going to call state 1, E naught is 0, it can be a 0 energy. I should call that S for state 1. That's S0. S1 we'll say has 1 joule of energy. S2 will give S2 3 joules. And S3 will give 5 joules. Well, we can just start playing around with the numbers and partition off energy until all of our energy is consumed and come up with any given state. Let's play with that for a second. If I wanted to, out of my 10 molecules, I could have 2 that are in state S3 with 5 joules. At that point, if I've got 2 molecules in state S3, all my energy is consumed. I've partitioned off all my energy, right? Or I could take something like 2 molecules and stick them in S2, consume 6 of my joules of energy at that point. Now I've got 4 left over, and I can take 4 molecules and stick them into state S1. Now I've got 2 molecules in S2, 4 molecules in S1. All of my energy has been partitioned off, and I'm finished, right? Or I could take 10 molecules and stick them in state S1. Just give 1 joule of energy to each molecule. There's a million different ways, something to the power of 2, different ways to give that energy out to my system. Of those arrangements, there'll be one arrangement that ends up being statistically the most likely arrangement. It's the most probable or mechanism for having your energy partition will correspond to a particular state. That is the state that the Boltzmann distribution picks out. The Boltzmann distribution says if we've got X number of molecules we've got X amount of energy, and we've got X number of states. What is the most likely arrangement that what's the arrangement that we're most likely to find our system in? You notice that when we were playing with this concept, essentially all we were dealing with was conservation of energy and conservation of mass. Conservation of mass. We just needed to make sure that our 10 particles were all accounted for, and that our 10 joules of energy, our 10 joules of energy and our 5 particles were accounted for. I was saying 10 particles for the last 10 minutes of lecture, so sorry for going back to what I said. Doesn't matter the numbers, just the concept that you've got a finite number of particles, and you've got a finite amount of energy that has to be dispersed amongst those particles, basically means we're dealing with conservation of mass and conservation of energy. And once you factor those into the statistical arrangement, conservation of mass and conservation of energy, you end up with this expression. What this expression ends up looking like graphically, oftentimes, is something like this. You'll have an axis, on the y-axis, population number of molecules at a particular energy level, and on the x-axis, you'll have the energy of each state. So this state right here has this energy, state I has this energy, state IC2 has that energy. And you'll notice that as the energy of the state increases, initially you'll have growth, and then you'll peak off at some point where you're dealing with the state that has the most molecules in it, or when I say state, I'm referring to these states, the energy states that have the most molecules in it. And then it'll trail off at higher energies. Most of the time, your tail of your distribution will fall off as you go towards zero energy. What that means is that for these systems, it's very unlikely to have a molecule that is at zero energy. Why, if you're trying to split a bunch of energy amongst a bunch of molecules, might it be unlikely to have any of the molecules at the zero energy state?
Well, the molecules that you're going to try to do transfer energy.
Yeah, if you got a bunch of energy dispersed amongst your molecules, those molecules are going to be kind of hungry to populate their lowest energy states, and so they'll accept energy into those states, and the majority of your molecules will contain some amount of energy. Right? They might not contain a lot of energy, but they'll contain some of it, and so it becomes very unlikely to find a molecule without any energy. You start to dump this energy in on top of your molecules, fill them up, and eventually you're almost out of energy. And so you're not going to have much energy left to give away. And so these higher energy states are going to end up being not populated. You won't need them. With a finite amount of energy, there's a lot of higher energy levels that might be available that will never need to be populated because you'll run out of energy before you ever populate. Right? And so that relates to this exponential dependence of the population number on the energy. As we go to higher energy levels, the distribution falls off. Let's draw two curves. Here's a curve at T1. What's the curve at T2 going to be? What's it going to look like if T2 is a higher temperature than T1?
Similar shape. So we shifted to the right.
So at T2, shift the temperature, you increase the total amount of energy that's available to your system. And so your distribution shifts slightly towards higher energy states. The population numbers of the higher energy states increases. Well, it seems kind of natural considering the argument we just presented, right? You've got more energy dispersed, you're gonna have to start populating those states. It's going to shift your distribution to the right a little bit. So an increase in temperature ends up shifting that distribution. So that's just the basics of the Boltzmann distribution. And again, it falls out of this statistical treatment where you're working with conservation of mass and conservation of energy, and you're just asking yourself, what is the most likely arrangement of energy that what's the arrangement that I'm most likely to find my system in? And that is the Boltzmann distribution. And so you can read this later. I just want to point out right here that when I was talking about conservation of mass and conservation of energy, mathematically, you don't need to know this, but mathematically what that looks like is the sum of the population numbers is equal to the total number of molecules in your population. That's conservation of mass. And the sum of the population numbers times the energies of the state ends up being the total energy of this system. So that's the conservation of mass, conservation of energy statements that were used in the derivation of the Boltzmann distribution. All right, so if we treat translational kinetic energy using the Boltzmann distribution, we can derive an expression that will allow us to calculate a couple of very important values. Those values are the average velocity of the gases in the system and the average square velocity of the gases in the system. And we'll see in a little bit why that's important, but suffice to say, those are terms that we're going to need to know in order to look at or to be able to predict the behavior of a gas system. Go back to our statement of the Boltzmann distribution. Number of molecules in state I is n over z, e to the negative v sub I over kt. If we're dealing with translational motion, then the value of that term e sub I is simply 1/2 mv sub I squared, right? Ke is 1/2 mv squared. And so your term for energy turns into a term with velocity. Okay. Plug that into our equation. And we get a big term that looks like this. Now when I jump to here, in order to get to here, I had to plug in a value for z. This is beyond thermo, this is stat mech, but I'm just going to tell you that z for this situation for motion in 3 dimensions is 2 pi kt over n to the 3/2 power. So again, we divide this by z, so that inverts, and we got m over 2 pi k to the 3/2 power right here, multiplied by n. The e to the negative 1/2 mv squared can be separated into x, y, and z components. And so we get this big term here. You don't, I want you to see this derivation. You're not going to have to do this derivation, so don't worry about it too much. You just watch what it turns into. We plug in our values. We separate velocities out into x, y, and z components. And now we've got a statement that says that if we want to figure out the number of molecules in a state I, then we integrate over the velocities relevant to that state I, and dvx, dvy, dvz, and we'll have a population distribution. This is not the easiest term to use. It's not the easiest way to cast this equation, in particular because we're not so much concerned in kinetic theory with whether particle is moving in x, y, or z directions, or what its velocity components are in the x, y, and z directions. We're mostly concerned with strictly how fast in total the thing is moving. And so you can switch pretty quickly from x, y, z coordinates to spherical polar coordinates, and spherical polar coordinates will recast this equation in terms of the absolute velocity of these particles. And once you've done that, just a heads up. Now that I'm thinking about it right now, I think that it would be really nice to ask a question about the Boltzmann distribution. It requires you to know that it was derived using conservation of mass and conservation of energy. So just plug that away over in your subconscious somewhere. You don't need to know this piece of math, but I want to show it to you. So a spherical polar coordinate system will have a velocity vector that sticks out in three-dimensional space, and it'll have some absolute magnitude that is the speed of the particle that it's traveling, and then it'll give you angles theta and phi that tell you where to move off of the axes as you direct that vector into its position that it takes in three-dimensional space. The conversions are that from x, y, z components to r theta phi, or v theta phi components are the vx is v total times sine theta cosine phi, vy is v total times sine theta sine phi, and vz is v cosine theta. Plug all those substitutions in, and you keep track of the fact that the absolute value of v is the square root of vx squared plus vy squared plus vz squared. Plug this stuff all back in together, you get this equation. Again, this is just the number of molecules in a state I that has velocity vi. It's 4 pi times n, m over 2 pi kt to the 3 halves, v squared, e to the negative m v sub I squared over 2 kt dv. This is the absolute number of particles. If you want to do that, if you want to turn that into a probability, you divide it by n, divide by the total, and that should have been an uppercase n. That was supposed to be big N, not little n. If you take n sub I over n, then that gives you the probability, right? What percentage of those molecules are in state I. This equation is equation 1.18 in your text, the Boltzmann distribution of molecular velocities. And so what it does is it just says, at a given temperature, how many molecules do you expect to be moving with a certain amount of speed? And really, it's a question of what is the energy of the state associated with that speed. Really, the question is, at a given temperature, how many molecules do you expect to have or possess a certain amount of kinetic energy, right? But it ends up being cast in terms of velocities,